Hello everyone. Today I'm going to talk about identification of hydrate by water content. This video is only the lecture part of the experiment. The actual experimental demonstration will be a separate video. Starting with the term hydrate, um, a very real life application of hydrate or example of hydrate is Epsom salt, which are used to make bath bombs, as can be seen in this image here. Chemically speaking, Epsom salt is basically magnesium sulfate heptahydrate. Now, magnesium sulfate is a very common chemical, but what makes Epsom salt different from magnesium sulfate is the presence of 7H2O there. This basically implies that there are water molecules present in addition to the magnesium sulfate, which makes it a hydrate. Now, magnesium sulfate is an ionic compound. Basically, what an ionic compound is two molecules or a bond which is formed as a result of transfer of electrons, which is happening right here in case of a sodium ion and a chloride ion, which transfers electrons from the sodium to chloride to form sodium chloride. Now, compounds which are formed as a result of ionic bonds are called as ionic compounds. And when we take ionic compounds and we try to look at the atomic arrangement of these, what we see is something like this, wherein chloride and the sodium ions, or the anion and the cations, are actually very systematically arranged because this is a crystal. This is also called as a crystal structure or a lattice structure. Now, this kind of a structure is very well known for ionic compounds, and these ionic compounds can be composed of either monoatomic ions, for example sodium and chloride, or aluminium over here, or it can also be composed of polyatomic ions, which we saw in the previous example of magnesium sulfate or sulfite here, or hydroxide or ammonium. Now, let's focus on the crystal structure of an ionic compound, taking this image as an example. What basically happens in a hydrate is, in addition to the ions present in the ionic compounds, there is also water molecules present or trapped inside the crystal structure of these salts or ionic compounds. As a result, the physical structure and to an extent the chemical structure chemical property is also different from its non-water counterpart. Mind you, the water molecules, they are not actually reacting with the salt or the ionic compound here. They are merely getting trapped in the crystal structure, or the gaps in the crystal structure. As a result, we don't call this as a reaction between them, but it's basically how the entity is existing, with the salt and the water molecule existing, or existing in a way that they are not interacting in a chemical nature. As a result, we cannot call this just magnesium sulfate, or we cannot just call it any kind of an ionic compound. We have to indicate the presence of the water, which is done here using the dot and the number of water molecules present. Now, I'm going to talk about what that number represents, but first of all, I want to talk about the nomenclature. Now, whatever number of water molecules is present there, it is accompanied by the term hydrate with it. So this compound will be called as magnesium sulfate heptahydrate. Now, if there was only one H2O present there, it would have been called as monohydrate, so on and so forth. Now, the number 7 indicates the number of water molecules present per unit cell of the ionic compound, or in other ways, number of number of moles of water per mole of the hydrate. That is what that number represents. We can see here this one unit cell has 1, 2, 3, 4, 5, 6, 7 water molecules, and that is why we write it as 7H2O. Now, this is what a hydrate is. Now, the goal of today's experiment is for you to understand how you can identify the hydrate, or you can determine the amount of water present in the hydrate. It's a very simple experiment. We start with the hydrate, which is in this case magnesium sulfate heptahydrate. This is how it looks kind of crystally, a little grainier. And then, because it's just water molecule trapped in the crystal structure, the hydrate is heated to an extent that the water molecules convert into water vapor and escape, and all you're left with is the hydrate minus the water, which in other words is also called as the anhydrous. You can actually see a very clear difference between the physical state. I mean, the physical state is the same, but this anhydrous is more powdered and hydrate is much more crystalline. As a result, the experiment is basically telling us to find out the water content by just measuring the mass of the hydrate, heating it, and measuring the mass of the anhydrate. This is what the experiment is gonna accompany. We have something called as a crucible. So crucible is a small ceramic container used in this experiment to where the reaction is happening. The reaction meaning the hydrate is getting heated enough to get rid of the water content. Now we have the basic heating apparatus here. We have a ring stand, we have a Bunsen burner, we have the crucible which I mentioned before, we have an iron ring, and we also have a triangle or a clay triangle meant to support the crucible on the iron ring. So once you watch the experimental video, you will get 3 observations. That is the mass of the empty crucible with the lid, mass of the empty crucible with the lid plus hydrate sample, and the mass of the crucible with the lid plus the sample after heating. So basically the experiment, what you're trying to do is you're taking amount of the hydrate, which is obtained by the difference between this and this. This is heated to an extent that you're only left with the anhydrate. That is what is being measured in here. And what is remaining, that is the difference between anhydrate and the hydrate, will give you the water molecule which is escaped, or which is actually converted into a water vapor. Note, this is how a chemical reaction is indicated. The sign here represents a heating sign, which is a very known in chemistry, and the reaction is always accompanied by the states of the reactant. Now, we start with the hydrate, which is in its solid form, and what we are left with is anhydrate, which is also again in the solid form, but the water molecule which is escaped, that's in gaseous form because it's getting converted into water vapor. Now, once you have all the data, we actually calculate the percentage of water content using this formula right here. We have the mass of water obtained from the values here. We also have the mass of the hydrate, which is here, and you multiply that by 100 to get the percentage of water content in the hydrate. Now this is how you calculate the percentage of water content experimentally. You're also supposed to actually find out the theoretical percentage water content. This will actually be one of the questions in your worksheet. So be very critical in understanding this part of the video. Basically, if we don't have access to an experimental way of finding the percentage of water content, we are also able to find out the percentage of water content by considering the molar masses of the compound here. Let's take an example of copper sulfate pentahydrate. Now, we are going to use the same formula, but instead of getting the masses from an experiment, we get the mass from the molar mass of the compound. So the molar mass of water here is 18.016 gram per mole, and in the case of copper sulfate pentahydrate, which is your hydrate, is 249.69 gram per mole. You can actually say that 1 mole of water weighs 18.016, right? Similarly, you can say the same thing for the hydrate, which will be 1 mole weighing 249.69 grams. Now, we have the mass of the water, we have the mass of the hydrate, which will be put in here. But remember that in this case, we have 5 moles of water, which means we have to multiply the 18.016 grams with 5, and then divided by the mass of the hydrate, which in this case is 249.69 grams. Once you do that, in this case we are getting percentage 36.08%. That basically means that 30% of the hydrate is or 36% of the hydrate is composed of water. So basically, this is the way you find out the theoretical percentage water content, and for experimental water content, you have the experimental values which I've explained in the previous slide. I hope this lecture helped you to understand the concept of hydrate and understand the methods to calculate the water content in the hydrate. Thank you.